Hello everyone, Gustavo here. So look, this topic is going to be super cool because it has everything to do with game physics, right? In our game physics course, we have been coding together and we have all these objects moving around with velocity, acceleration. So physics step by physics step of our simulation, we have been updating their position so they move around the screen. We have an issue. What happens if these rigid bodies collide with each other, right? As they are moving, changing position, velocity, what happens if we find an overlap? We need to resolve this collision, right? And if you think about what happens in the real world, if you have these two rigid bodies, right? If they have velocity of body A and velocity of body B, right? These velocities pre-collision, we need to calculate and we need to probably change these velocities. So the object A goes one way and the object B goes the other way, right? So we are going to apply what we call the impulse method, meaning that we're going to apply an impulse to body A and B, probably plus impulse and minus impulse, right? So they go their own direction. And everything has to do with this information, right? The velocity of A, velocity of B, and based on that collision, that overlap that we identified, we're going to have the penetration depth, right, of that collision, and also what is the normal of that collision. So we're going to have this normal vector of the collision that we calculated by that overlap. Based on this, we're going to calculate what is the magnitude of the impulse vector that we have to go and apply to bodies A and B. All right, so this quick lecture right here has everything to do with us calculating, right, the math, break down the math of finding the impulse vector magnitude. What is the value of the magnitude that we have to apply to bodies A and B to go and solve that collision, right, resolve that collision in a way that that is similar to what we expect to see in the real world. So the question now is, how do we calculate the impulse magnitude J? And I'm calling the magnitude J just because of kind of impulse, right? What is the magnitude of that impulse vector J generated when those two bodies collide? So we have those two bodies, they overlap each other, we found that collision information, we have the normal of the collision, we have the penetration depth, and to calculate the magnitude of that J, we need to take into account the velocity pre-collision of both A and B, right? So if they were traveling with these VA and VB velocities pre-collision, we need to take into account that conservation of momentum and then the velocities post-collision and these impulses that we're going to apply to A and B, we need to take into account these velocities, right? And let me just write this thing down. The impulse vector is generated by the velocity at which the two bodies collided. So we need to take into account the velocity, right? The pre-collision velocity, VA and VB. But what we are really interested in is the relative velocity of those two objects. And I'm going to use this VREL here, right? The V with the subscript rel. So what we really want, whenever we talk to each other about relative velocity, it is the difference between the velocities of A and B, right? So I think everyone understands that we are talking about, right? The relative velocity between those two objects is the subtraction between the velocity of the first and the velocity of the second. And if you want to kind of put things into context, if you have, for example, if I'm riding on a road, right, and if I'm kind of driving on this road at 100 kilometers per hour, and if I have another car beside me that is also riding at 100 kilometers per hour, the relative velocity between my car and that other car is 0. The difference between my velocity and that other car is 0. And if that car goes a little bit faster, so if they go, let's say, 110 kilometers per hour, then the relative velocity is 10 kilometers per hour. So with this in mind, right, thinking that what we are really interested in, right, to calculate this impulse magnitude is we have to look at the relative velocity between those two objects. Let's just go now to the next slide and let's look at this problem. That is what we have. That is our problem statement. Two objects, we collided, right? There's a little overlap. We have the penetration depth. We have the normal of the collision. And we do have the old velocity pre-collision VA and VB, which will give us the relative velocity of that collision. given that we have that relative velocity, I want us to think about this. I need to get that relative velocity along the normal, right? So I'm interested in the relative velocity of those two objects, but along the normal vector, right? So when I say along the normal vector, we have to probably get that relative velocity and project along the normal. So what we are really going to use is the relative velocity dot product normal, right? The unit vector, the normalized normal vector of that collision. Does that make sense? We are interested in the relative velocity of the collision along the normal, right, of that collision. We are only interested in the thing in the direction of the normal. Right, so I'm just kind of putting all the pieces that we need to solve and derive the magnitude of the impulse j that we need to apply to bodies A and B. Right, and now if you look here, I have that scary formula underneath. Don't worry, I'm going to explain what that formula really means. This formula right here has to do with a concept that you probably studied before, which is the idea of the elasticity of that collision. Remember whenever we, probably in elementary school or high school, you studied this concept of perfectly elastic collisions or inelastic collisions? I have now that minus e. Look, that minus e has to do with something called the elasticity of our collision. So the new relative velocity, right, the v prime rel there on the left, dot product with normal, is equal to minus epsilon multiplied by the old relative velocity dot product normal vector. That minus epsilon right there, this is what we call the coefficient of restitution of our collision. And that is going to be a value between 0 and 1, which will determine the elasticity or the bounciness of that collision. So different materials, right, different bodies, they will have different coefficients of restitution. And that coefficient of restitution is basically how elastic that collision is going to be for that body. So if I have a basketball, the coefficient of restitution is pretty high. It's probably around 1.0. But if I have a ball of clay or mud, that thing is not going to be elastic, right? It's just if something collides with that ball of clay, things are not going to bounce. It's not going to be an elastic collision. That ball of clay is probably going to have a coefficient of restitution 0 point something, right? It's going to be non-elastic. This thing right here, that epsilon, has to do with the coefficient of restitution. And you're going to see this coefficient of restitution as this measurement of how elastic is going to be that collision for that particular system. I will claim that in our body class, we're going to have a coefficient of restitution for that body. So each body will have a different coefficient of restitution between 0 and 1, and if it is 1.0, that collision is going to be totally elastic. And if it is 0.0, that body, that collision is going to be completely inelastic, so we're not going to bounce. These objects are going to stay together. Does that make sense? So that formula says that the new relative velocity has to do with the multiplication of minus that epsilon coefficient of restitution, that elasticity factor, times the old relative velocity dot product n. All we introduce there is the minus epsilon value between 0 and 1, which is this kind of percentage of coefficient of restitution. All good? Easy, right? So I just want to now plug as well, we need to take into account this coefficient of restitution, this elasticity of our collision. Right, one more factor that we're going to have to take into account when we calculate the impulse of the magnitude of the impulse that we have to apply to A and B. Let's start talking about our problem. Let's start to derive, with all this information at hand, let's derive the formula to find the impulse magnitude that we have to apply to these bodies that are colliding. The first thing that I want to point out is this. We have been speaking about momentum, right? As these objects collide, the momentum before the collision needs to maintain and be equal to the momentum after the collision, the conservation of momentum, right? And remember that the momentum, right, the difference of momentum of A and B Momentum is mass times velocity. Right? So look at the difference of momentum A and B. The difference of momentum post-collision and pre-collision, I am saying that it is the mass of A times the new velocity of A minus the mass of A times the previous velocity of A. So the new velocity minus the old velocity. That is going to give us the difference of momentum of A. And I'm also putting down the difference of momentum of object B. So the difference, the delta momentum of B, is mass times new velocity of B minus mass times old velocity of B. Mass, velocity. And pay attention that the mass is not changing, right? The mass of the object pre-collision is equal to the mass of the object post-collision. That is why the only thing that is changing between the difference of momentum is my velocity. The new velocity A, old velocity A, new velocity B, old velocity B. Easy? And let's move forward. We know that the difference of momentum, we have a name for that. That is impulse, right? So the difference of momentum, old and new in this case, that is going to be the impulse that we're going to change in our system. And look at what I'm using there. I'm saying Jn equals to MAV nu A minus MAVA. Jn, that J unit vector n, that is my impulse vector, right? That is the delta P, the difference of momentum. That is going to be the impulse along the normal, right? In the direction of the normal. You can read that Jn as J is the magnitude of the vector impulse, and n is the direction, right? The normalized direction of the impulse vector. It's almost like I am scaling that normalized vector by the J scalar. So Jn is the impulse vector, magnitude and direction. Because we know, right, intuitively, we know that the direction of the impulse is along the normal, is in the direction of the normal vector. So Jn is the impulse that we have to apply to A. But also we have a minus Jn for B. And here is where I have to start thinking about the conservation of momentum, right? Minus A or plus Jn minus Jn to B. So that means plus 2A minus 2B. So I just flip the intensity, the magnitude of that vector by minus Jn. So now these two formulas are super important, and they are going to start, we're going to use them to start deriving what is the J. That is what we want to find, right? We want to find the magnitude J of that impulse that we have to apply, and then we go and we apply to bodies A and B. Very well. So let's start and let's keep going, right? Let's just do some simple algebra right here. I am going to now I want to find everything in terms of the new velocity A and the new velocity B. What is the velocity, right? The new velocity post-collision of A. It is the old velocity A plus Jn, the impulse, divided by the mass. And the new velocity of B is Vb minus Jn divided by the mass of B. I hope this makes sense, right? Only simple algebra, but if you stop and you look at the formulas, they make sense. The new velocity is the old velocity plus the impulse that I apply divided by the mass, right? So inversely proportional with the mass of A. The bigger the mass, the less is going to be the new velocity. And Vb is equal to the old velocity B minus the impulse divided by the mass of B. Again, inversely proportional with the mass of B. The bigger the mass of B, the less is going to be the new velocity of that post-collision that I need. Right? I wanted to start exercising these ideas of looking at the formula and not looking only at the symbols. Think about what goes behind that explanation, right? Look at this inversely proportional relationship between these things. The new velocity is the old velocity plus the impulse divided by the mass. Think about what that means in terms of real world, right? What do you expect to see? Does this make sense? I think it does. Very well. So this is super important, the new velocity A and the new velocity B, right? These velocities. What we are interested in is that relative velocity, right? So we have the relative velocity, which is the subtraction between these two new velocities. What is that? Well, we know that the new relative velocity along the normal is equal to the new VA minus new VB along the normal. So relative velocity is the subtraction between velocity A and velocity B. So I am going to subtract VA new minus VB new. So I'm going to subtract these two things right here, and let's just go ahead and do that. The new relative velocity, which is going to be the subtraction between new VA minus new VB. So if I subtract this minus this, let's see what this new relative velocity is. It's going to be this minus this, so VA minus VB, VA minus VB, and then I have to subtract, so plus minus minus, that is going to be plus, so plus Jn divided by MA, minus plus, right? So plus minus plus Jn divided by Mb. This thing right here is simply this line minus this line. I just subtracted these things, right? So this minus this is what I get. This is what we need to start thinking about and finding this impulse magnitude J. Eyes on the prize. What we want is to find the impulse magnitude J. So we are probably going to have to isolate this J there and try to do some algebra tricks to isolate this J on the other side to find everything in terms of this relative velocity. Correct? So what is the next step here? Well, I think that the next step here is to consider that idea that we want everything along the normal vector, right? So everything dot product n, I want everything along the normal vector. So this new relative velocity has to be dot product n. And all these things right here, dot product n again. So I am going to have to take the dot product n of everything, which means that I'm going to have the new relative velocity dot product n is VA minus VB, that is the relative velocity, the old relative velocity dot product n, right? So this is, I just replaced this thing, VA minus VB, the old relative velocity dot product n, plus this whole thing right here, dot product n, right? Everything dot product n. So I just added this dot product n with all my terms. This is what I want. Everything has to be, I always have to think about things along the normal, right? That is what I want, the impulse along the normal vector of that collision. So dot product and everything. And now it's just a matter of doing algebra, right? It's just kind of distributing everything, factoring things out, and doing actual algebra tricks. Right, so let's see what we have. I think I can basically factor a couple of things out. So maybe this Jn, right, this magnitude and the direction of the impulse vector, maybe I can, since I have them in both terms, I can factor them out, right? Maybe I can just pull it out. And also, do you see how I have that thing that is called V new rel dot product n? The new relative velocity dot product n, we know that we have to take into account this thing right here. So let's plug the coefficient of restitution here as well. So the new relative velocity dot product n has to do with the old relative velocity dot product n multiplied by this negative coefficient of restitution, right? This factor that we have to multiply that tells us how elastic or inelastic our collision is. So let me just replace that V new rel dot product n with this formula right here. So just replacing this thing with this thing right here. And then equals to, I didn't change anything, so vrel dot product n, the same thing as before, and then plus, and here is where I did what I told you, right? Since I had jn here and jn here, I just kind of factored that jn out, I pulled it out of this multiplication, and then I multiply jn by 1 divided by ma plus 1 divided by me. So this thing right here is multiplying these both terms, dot product n, still. See, simple algebra, right? If you want to do this pen and paper, go ahead and pause and do it yourself. I think it is important that you do these things yourself. Simple math. Well, I'm saying simple math, but you and I, we know, right? This is important, right? To go and dissect this thing. Nothing is simple, right? There is always, the devil is always in the details. Cool, so what can I do right here? Well, I have all these things. I think I can pretty much start thinking about what I really want. What I really want is, we are interested in this j, right? This is what we want. We want to find the magnitude j of the impulse vector that we have to go and then apply to bodies A and B. So I think it is wise for us to start isolating this j, maybe on the left side. And I think that's what I'm going to do right now. I'm going to say that j, so I'm going to put this j on the left, and I'm going to put everything else on the right, right? Bringing everything that was on the left to the right, so isolating that j, the magnitude of the impulse vector that I need. So j goes on the left, and then I'm just subtracting, right? I'm sending this vrel dot product and subtracting on the other side, so minus vrel dot n, and then everything right here goes dividing, right? So everything that I have here, this multiplication of n multiplied by this thing dot product n, I go and I send dividing on the other side. So this is what I have, right? I have the j, which is now in terms of the coefficient of restitution, that sigma, that epsilon value that I have, vrel dot product n minus vrel dot product n, everything divided by what was multiplying j before, which was n dot product n divided by 1ma, 1 divided by mb. Algebra, right? Simple, simple algebra. Algebra 101. And we are almost there, right? I think what we want is, we want everything in terms of this old relative velocity. So I think we can even simplify this whole thing right here. Since we have multiplied vrel dot product n and vrel dot product n, we can factor this out again. So I think we can simplify the numerator just to be in terms of vrel dot product n and then minus epsilon, the coefficient of restitution. I think we can simplify it by this thing right here. So this thing on the numerator is just us factoring things out, and then I just kept the denominator. This right here is what will give me the impulse magnitude j that I have to apply to my bodies A and B. But just wait a minute, because do you see this denominator right here? There is something else that we can simplify. Do you see this n unit vector, dot product n unit vector? And I'm going to propose an exercise here. Think about what that means. We can simplify even more this denominator right here, because think about what it means for us to get a vector, a normalized vector, meaning length 1, and dot product with itself. What is that? If I have a vector, and we know that this thing is a normalized vector, it is a unit vector. If I have one vector and I take the dot product with itself, what is the result of that? And I want you to pause the video. I'm going to give you 5 seconds. What is the answer? How can we simplify this thing even more? So go ahead, 5 seconds, and I'll be back very soon with this simplification in the denominator as well. So, easy, hard, did you get it? If I have a vector, and we know that it is a unit vector, it has length 1. If I take the dot product between a vector that is length 1 with itself, what is this result of the dot product? Well, we can basically just think about this, right? If a vector is length 1, and I take the dot product with itself, the projection of a vector length 1 with itself, the result is going to be 1, right? It's going to be 1.0, the scalar value 1.0. So the result, right, the value of the dot product of a unit vector with itself has to be 1.0. So if I multiply everything by 1.0, I can basically just simplify it, right? It's not going to change anything. I can basically simplify. It's going to be 1 divided by ma plus 1 divided by mb. That's it. So that thing cancels out, is 1.0. Anything multiplied by 1.0 is that thing. Good stuff. So I just want to point out that if we know that this normal vector right here is normalized, if we can guarantee that it is length 1, and we can because we are always normalizing that normal of the penetration, right? We're always normalizing that vector before anything. So if we can guarantee that this thing is normalized, unit vector, we can simplify the denominator as well. And this is the final formula. Ooh, we finally got it, right? This is the formula that we're going to use, and we're going to plug in our source code to go and find the impulse magnitude J. And I already wrote that down. J is the impulse magnitude, right? Is the vector impulse magnitude that we have to apply along the normal direction to the bodies that just collided. And again, we are probably going to apply plus J to A and minus J to B to send A one side and B to the other side, right? To kind of have this conservation of momentum that we need, we have to apply minus and plus. Good stuff? So this right here is the formula that we're going to use in our source code to calculate the impulse vector magnitude that we have to apply to A and B, plus and minus. Let's go ahead and let me give you a spoiler of what I think the source code is going to look like. This is going to be just a snippet of code that I'm going to show just to kind of already create some skeleton of the source code for us to apply and find this Jn. Do you see how I'm calling it Jn? Jn is going to be the impulse along the normal vector direction, right, that we have to apply to these bodies that just collided. So I'm going to use this thing Jn. That is going to be the magnitude of my J along the normal. Source code. I will have in my collision class, remember the collision class, I have this resolve collision, which I'm going to pass the contact that has all that information of the normal of the penetration depth, the bodies A and B. So contact is the contact information that I receive via parameter, right? It has that contact information. And then in the resolve collision, I'm going to resolve the collision by using the impulse method, right? This is what we're creating. We are creating a solution. We are resolving our collision to bodies A and B overlap using the impulse method. We're going to apply an impulse to body A and minus impulse to body B. How do you do that? Let's just see what I did. So I am just kind of fetching from the contact the pointers to body A and B. So I have body A and body B of my penetration, of my collision. And right here, I am already going and defining the elasticity of this collision, of this system. This is going to be based on the coefficient of restitution epsilon. Where does this thing come from? Well, I am creating a float, epsilon, which is going to be this value between 0 and 1, and the float epsilon, this float E, is going to come from the minimum value between the restitution value of A and restitution value of B. So let's just say that we're going to have both bodies A and B, they will have their own restitution value, right? The coefficient of restitution. So what I'm interested in, and the way that I'm solving this is I'm saying, get the minimum between those two values. And if I stop to think about this, I think intuitively it makes sense. I like to use the minimum between these two values because, think about this. If you have a rubber ball that is very elastic, right? And if you have a ball of mud that is completely inelastic, what do you expect to happen when this ball of rubber hits the ball of mud? I think it's going to be inelastic, right? The ball of rubber is going to kind of just stick with that ball of mud. So I'm always going to take the minimum between those two restitution coefficients. Does that make sense? That is how I approach this. You will see that different physics engines, they approach this differently. I am just going to take the minimum. I think it's fine from what we want to achieve. Float E, that is my coefficient of elasticity, the coefficient of restitution. Let's go and proceed. I need to find the relative velocity. Easy, right? The relative velocity of this system, of this collision, is A velocity minus B velocity. That is going to give me this relative velocity vector with the subtraction between A minus B. Easy as well. And then all the derivation, all that formula, all that math breakdown boils down to these two lines right here. I proceed now to calculate the impulse vector along the normal. So I divided my vector between impulse magnitude, and then I calculate the impulse direction. We know that the impulse direction, the second line, impulse direction is going to be my contact normal, right? That is the direction of the impulse that I have to apply. So the direction is easy. The impulse magnitude, my J that I just calculated, comes from that formula right there. So if you look right here, I'm just translating that formula from mathematics notation into source code C++ notation. So the impulse magnitude J comes from minus 1 plus coefficient of restitution E times the dot product between the relative velocity and the normal. So the dot product between the relative velocity and the contact normal, easy. And then everything divided by 1 divided by MA plus 1 divided by MB. And do you see how we have it's very easy because we already have the inverse of the mass of A and the inverse of the mass of B. I keep repeating myself again and again. This is why you will see most physics engines store in the bodies A and B the inverse of the mass. And this is an example of why that is useful. Another formula that we have to take and calculate things using the inverse of the mass of my objects, right? The inverse of the mass, super useful. We see it again here whenever we're calculating the impulse method. Cool, so I have now the impulse direction, I have the impulse magnitude. How do I find the result impulse Jn, right? This vector 2 is the Jn, which is, I just kind of combine both magnitude and direction. So the final Jn, my impulse vector, is the impulse direction scale impulse magnitude. Right? So if I get that direction, that normal vector, and I scaled by the magnitude, if I just multiply it, right? I scale by the magnitude, that is going to give me the final impulse vector. And then all I have to do is say, body A, apply the impulse Jn to A plus, and apply the impulse minus Jn. I just flip that vector and I apply the negative Jn to B. So plus Jn to A minus Jn to B. And this thing right here, as soon as I apply that impulse and I go and I change that velocity, remember that applying impulse means an instantaneous changing the velocity of the objects. As I apply those impulses, I hope to see these bodies colliding and then going their own way because I'm applying different impulse to them, right? A goes one way, B goes the other way. And this is it. Whew, I told you this was a long lecture, but I think everything makes sense, right? This is the math, this is the breakdown that we need to find this big formula right here that has to do with the impulse, the linear impulse that I have to apply to A and B to solve this collision, right? To resolve this collision. And I don't know about you, but I think this topic right here of resolving collision, right? Linear collision resolution is super cool. And I want to ask you one question before I say goodbye. Can you please write down in the comments do you know any games that only uses linear collision resolution to solve the resolution of the collisions of the game? I know, for example, there was a game that I used to play a lot. It was called The Incredible Machine. And The Incredible Machine, you have all these objects. There is this physics ideas of gravity, velocity, acceleration. But I wanted to pay attention to what happens to the ball. Do you see how the ball, as it collides, it doesn't change its rotation? It only changes the linear velocity. Right? So there is no rotation involved. This is what I mean when I say that we are only resolving this collision using linear collision resolution, right? We are only interested in the linear impulse that we apply, not rotation. So The Incredible Machine was one example. If you know another game, and if you can think of another game that uses only simple linear collision resolution on how to resolve collisions, just write down in the comments. I always like to get more examples of games that use linear collision resolution using the impulse method. Right? So if you like this type of content, thumbs up, subscribe. Right? Don't forget to subscribe if you like contents like this. And remember that this whole thing right here is part of a comprehensive course on game physics that I teach at pikuma.com. So don't forget to go there. It will be super cool to have you as one of my students, where we go and we create a physics engine from the ground up, right? Using C++, we code together and we create this physics engine, this very simple physics engine, understanding all this math, all this nice physics that goes behind these ideas of game physics, right? It will be super cool to see you there. All right, thank you very much. See you soon.